Hello. Today in calculus we are going to learn about average rate of change and how that relates to something called the derivative. So the average rate of change, or AROC if you want to do it that way, is essentially the slope. It's going to be f of b minus f of a over b minus a. So let's kind of look at an example here. The Princeton Dinky is the shortest rail line in the country. It runs for 2.7 miles, connecting Princeton University to Princeton Junction Railroad Station. The Dinky starts at the university, moves north to Princeton Junction. Its distance from Princeton is shown in the graph, where t is time in minutes, and the distance s, the Dinky, from Princeton University in miles. So here's Princeton University. Here's the junction, 2.7 miles away. Okay, so this is giving us position. So when is the Dinky headed towards Princeton University? Okay, so Princeton University is here. It's going away from Princeton University, and then it's heading towards here and here. But there's this little place where the position isn't changing. So from 7 to 10, so from 10 to 11, we're taking a little break. So then from 11 to 13, we're headed towards the Princeton University. When is it headed towards Princeton Junction? It's right from here to here, so that's 0 to 4. Okay, when is it stopped? Okay, well, stopped means it's going to be at the same position. So from 4 to 7, and then again from 10 to 11. So find the average velocity of the trip from Princeton to Princeton Junction. Okay, so from here to here. Well, the average velocity is going to be the change in distance, say d, over the change in time. So in this, we're going 2.7 what are the units? Miles in 4 seconds. Minutes. Okay, which if you type that in the calculator is 0.675 miles per minute. Okay, but I want to point out here that it's not going to be going that the whole time. So if you see here, it kind of is a little curve here and a little curve here, and we're going to talk more about that. Okay. A drag race is 1,000 meters long. A certain car completes the race in 5 seconds. So what is the average rate of the change of the car from 0 to 5? Well, he's going 1,000 meters in 5 seconds. So that's an average rate of change of 200 meters per second. Okay, is the car traveling that speed the entire time? No, you don't just go instantaneously to 200 meters a second. Okay, so it's going to start off slower and then steadily speed up to that. So let's think about that, how that would represent graphically. Okay, if this is this is time, and this is our position. Okay, let's put 5 seconds here and 1,000 meters here. So thinking about what's happening here, he's going to start off going slow, so the position is going to change, but as he speeds up, we get faster. Okay, so the average rate of change is the slope of this line. Okay, we'll call that a secant line. So this is the average rate of change, but the speed here is different than the speed here. It's going to be less than 200 here, more than 200 when we get to the end of the race. Okay, so what we can use, given the graph of the position, how would you find out how fast the car was traveling at t equals 3? Okay, well at t equals 3, the slope of the tangent line is going to represent the speed. And this leads us to the idea of the derivative. The derivative. This is extremely important. We're going to spend about half a year talking about the derivative. So we're going to talk about different interpretations. The derivative geometrically is going to be the slope of the tangent line. Okay, the rate of change interpretation is it is the instantaneous rate of change. Okay, so back on my graph, if I wanted to know the speed at the instant when time was 2, that's the derivative or the instantaneous rate of change. Okay, the physical interpretation, if S of t is the position, the derivative is the velocity. Okay, the rate of change of position is velocity. Notation. Okay, for a little bit, this notation is going to feel kind of funny. After a while, it'll be second nature. Okay, one very common way to represent the derivative is dy dx. Okay, and this is going to come from the idea of slope, where if I had slope would be delta y over delta x. Okay, dy dx is an instantaneous slope. It's the slope at a single location. Some other notations for the derivative, and again, right now these are foreign to you, but you'll have them down. F prime of x, if I have a function and I want to take its derivative, we'll use that little prime. Same if I've got y, if I wanted the derivative, we're going to have y prime. Okay, so derivative again is the slope of the tangent line, so an instantaneous slope, instantaneous rate of change, and velocity if it's position. Okay, we will get so many examples you will understand as we go through this. All right. A tire is punctured by a nail. As the air leaks out, the distance y inches between the rim and the pavement depends on time, t. Since the tire was punctured, values of t and y are given in our chart here. Okay, what is the average rate of change on 0 to 12? So that's going to be f of 12 minus f of 0 over 12 minus 0. In the chart, that's going to be 3.26 minus 6 over 12, which if you type this into the calculator is going to be negative 0.228. The units are going to be the units on the top over the units in the bottom. So the units on the top are inches. Units on the bottom are minutes. Okay, now we're going to use the data in the table to estimate the instantaneous rate of change at t equals 6. Okay, because if you look at these values, ideally we'd have values that were really, really close to 6 to estimate that, but this is what we're going to work with. So the instantaneous rate of change, so I'm going to use that notation. So the instantaneous rate of change, or the derivative at 6, is going to be approximately equal to, because we're just doing an estimate, f of 8 minus f of 4 over 8 minus 4. So that's going to be 3.76 minus 4.42 over 8 minus 4, which if you type that into the calculator is negative 0.165. This again is inches per minute. Okay, so it says Using correct units, interpreting the meaning of the instantaneous rate of change at 6 in the context of the problem. Okay, so the instantaneous rate of change in this problem, the distance between the rim and the pavement, okay, is decreasing because it's negative at a rate of 0.165 inches per minute at t equals 6. So that's saying at that time, that's how fast the air, that's how fast the distance is changing. And in this case, the distance is decreasing because the rim's getting closer to the pavement. The graph shows the temperature T in degrees Celsius of a kettle of water at time X in seconds since the burner was turned on. So the temperature, burner's turned on, gets to 100 degrees Celsius, stays there a little bit, and then decreases. So it says draw tangent lines to the points where x equals 40, x equals 100, and x equals 140. Use the tangent lines to estimate the instantaneous rate of change of the temperature at these times. So at 30, my trusty hall pass from 2015. Okay, so the slope of this line is going to be the instantaneous rate of change at 40, so t prime of 40. Okay, so using, let's see, we're going up. So keep in mind these are going up by tens. So maybe we're going up 1, 2, 3, and over one block here, which is, these are each 20. So this is approximately equal to rise of 30 over a run of 20. And as long as you have something close, that's fine. So this is approximately 1.5 degrees Celsius per second. So at that point in time, the water is heating up at that rate. Okay, what about at 100? Well, the slope there okay, we've reached 100. It's not going to go above 100 because when water boils, it hits 100 degrees and it stays there while it's boiling. It doesn't get any hotter. So T prime at 100 is going to be 0 degrees Celsius per second. There is no change in the temperature. The temperature is remaining constant. Lastly, at 140, okay, so T prime at at 140. Okay, we're going down maybe 20 and over 20, about. Doing about. So negative 20 over 20, which is going to be 1 degree Celsius per negative 1 degree Celsius. Okay, so it's negative because the temperature is now decreasing. Okay, and we've kind of already talked about all this, but what do you suppose is happening for 0 to 80? Oh, the water's heating up. From 80 to 120, we are boiling and the temperature is not changing. And then from 120 on, it is cooling down. Okay, so how do we find the slope of a curve? There's two different formulas that we're going to use for that, so I'm going to derive each of them. Okay, so the first definition, let's look at what we're trying to find. I'm trying to find the slope of a point on this curve. Okay, which is going to equal to the slope of our tangent line. Okay, well, I can't find the slope if I only have 1 point. We need 2 points to find slope. Ask any Algebra 1 kid. Okay, so I'm going to pick another point out here. Okay, and we call that a secant line. So I'm going to call, let's get back here. This is going to be C, which makes this F of C. and just for our convention, I'm going to call that x, which means this is f of x. Okay, the slope of the secant line is going to be y2 minus y1, so this is x f of x. This is c f of c. So y2 minus y1 over x2 minus x1. So f of x minus f of c over x minus c. That is the slope of the secant line. Easy. Okay, the slope of the tangent line is here. So what we're going to do, I can find this slope, is I want this x to move as close as possible to that c. Well, the tool we have to do that is limits. So the slope of the tangent line is going to be the limit as x goes really, really close to c of the slope of the secant line. So that's our first definition. Second definition. Okay, let's put our point here. This time I'm going to call it A, no particular reason, which makes that f of A. And if I want the slope of the tangent line, so let's go ahead and draw our tangent line. Okay, we're going to do a similar idea of I'm going to put another point on this line. How we do this, though, is going to be a little bit different. Okay, so I'm going to say that this distance is h, or on the graph from here to here is h. So if this is A and this distance is h, this is A plus whatever h is, which means this is f of A plus h. Okay, well, the slope of this line is going to be y2 minus y1 over x2 minus x1. So in this case, okay, so this would be the slope of that line. Okay, is going to be f of A plus h minus f of A over A plus h minus A. Okay, well, this A is going to cancel with this A, so we're going to have this over h. Well, how do we get the slope of the tangent line? Well, in this case, I want h to be as small as possible. Okay, so the slope of the tangent line is going to be the limit as h goes to 0 of f of A plus h minus f of A over a simplified denominator of h. So that is our second definition for the tangent line. Okay, so find the slope of the curve y equals x squared at the point 2, 4. I'm going to use both definitions just to show you that we can. Okay, starting with our first definition. Okay, c in this case is going to be 2. That c in this equation and a in this equation is the location that we're interested in. Okay, so we're going to have the limit as x goes to 2 of f of x minus f of 2 over x minus 2. Now this should seem familiar. We have done this before. So we have the limit as x goes to 2 of f of x, which is x squared, minus f of 2, which is 4, over x minus 2. If we plug in 2, we get 0 over 0, which means we got to do some math first. So we will factor. So the x minus 2's go away. now we have the limit as x goes to 2 of x plus 2, which is 2 plus 2, which is 4. Okay, the slope of the tangent line on the parabola y equals x squared at 2, 4 is 4. Okay, now I'm going to do this whole thing again with the other definition. Okay, so I'm going to use this. A, in this case, is my 2. So we're going to have the limit as h goes to 0. In that formula, that's always what we're looking at. So f of a plus h is 2 plus h minus f of 2 over h. Okay, well, our f of x is x squared. So f of 2 plus h is going to be 2 plus h squared minus f of 2, which is going to be 4 still, over h. Okay, so I'm going to expand that. So that's going to be 4 plus 4h plus h squared minus 4. Okay, well, the 4's are going to drop out of this. And what we're left with is things that have h's in them. So I'm going to divide that by h and that by h. Which will leave me with 4 plus h over h is 4, and h squared over h is h. As I go to 0 is 4, which is excellent news since it's the same as what we got from this formula. So either formula works just fine, and we will be coming up with actual rules to find these derivatives, but right now we're using limits. Now we're going to follow a follow question. So let's find the equation of the tangent line. We're going to be using the point slope form of a line very frequently. So y minus y1 equals mx minus x1. Okay, so we have the point and the slope. So y minus our y value 4 equals our slope 4, x minus 2, and we are just going to leave it like that. The normal line is the perpendicular line. Okay, so the only thing that's going to change is the slope. Okay, the slope of perpendicular to 4 is negative 1/4. Okay, now I'm going to graph f, the tangent line to f, at 2, 4, and the normal line. So we'll make our grid. Here's f of x, just x squared. The tangent line has a slope of 4. The normal line is going to have a negative 1/4. It's going to go right through that same point, just perpendicular. Okay, this question is asking us the same thing in different language. Find the derivative of the function 2x squared minus x minus 7 at x minus 1. Okay, we are finding the slope at x equals 1. I'm going to again use both definitions. You might give it a try it yourself before we go. Okay, our first definition, we're going to, negative 1. Okay, so as x goes to negative 1, so limit as x goes to negative 1 of f of x minus f of negative 1 over x minus negative 1, which would be x plus 1. So f of x is 2x squared minus x minus 7 minus f of negative 1. If I plug negative 1 in here, okay, and I know you guys know how to do that, so I'll just tell you it is negative 4. So minus negative 4 over x plus 1. And we just sort through the algebra of this. -1, 2x squared minus x, -7 minus a -4 is a -3. Okay, again, we're going to need to factor. X plus 1 better be one of the factors, which means 2x minus 3 is the other one, and you can double check to make sure that middle term works out. Okay. So we have limit as x goes to -1. These guys go away, so just 2x minus 3, which is 2 times -1 minus 3 is -5. Okay, we're going to do this again with the other definition just to show that it works. Okay, so our second definition, the limit as h goes to 0 of f of h, f of -1 plus h minus f of -1 over h. Okay, so we're going to take -1 plus h and plug it into each of the x's here. So we're going to have to write kind of small. So 2 -1 plus h squared minus -1 plus h minus 7 minus the -4. Over h. So we've got some algebra work to clean this up. I'm going to FOIL this and simplify some things here. So we're going to have 2 times, if I FOIL this, -1 times 1 is 1, and then we'll have minus 2h plus h squared plus 1 minus h when we distribute that negative. And then -7 minus -4 gives me a -3. Okay, distribute through the 2. So 2 minus 4h plus h squared. We can go ahead and combine those. So minus h minus 2. Okay, so the 2's cancel, and then I've got a -4h and a -h. So -5h plus h squared over h. H is reduced. So -5 plus h as we go to 0 is -5, just like we saw with the other definition. Okay, final example. The equation for free fall on the surface of Mars is S of t equals 1.86 t squared meters with t in seconds. Assume a rock is dropped from a height of 200-meter cliff. So how long does it take for the ball to hit the ground? Okay, so this is our position, which means we're looking for when does our position equal 200. Okay, if I solve that equation, divide by 1.86 and take the square root, 370 seconds. Okay, so that's how long it takes to drop from a 200-meter cliff. What is the average velocity? Well, the average velocity, we're going 200 meters in 10.370 seconds, which is about 19.286 meters per second. For AP, always 3 decimal places. So 3 decimal places, 3 decimal places. Okay, find the average velocity from t equals 1 to t equals 3. So we'd plug those in, so you'd have 1.863 squared minus 1.861 squared, which when you plug that in is 7.44. Again, this is meters per second. Oops, sorry. Okay, find the velocity of the ball at t equals 1. Okay, so this is asking us to find the instantaneous rate of change at a single location, which means we're going to use the slope of a tangent line formula to find that slope or the rate of change at that instant point. Okay, I'm going to use the first definition. Okay, so we're going to look at the limit as t goes to 1 of s of t minus s of 1 over t minus 1. Okay, so that's going to be the limit as t goes to 1 of 1.86t squared minus 1.86t. Okay, well, I can factor out the 1.86t, which will leave me with t minus 1. So this whole thing so we'll have 1.86 factored out, and then t minus 1, and then t plus 1. Okay, the t minus 1s will go away. So we've got the limit as t goes to 1 of 1.86 times t plus 1. So when we plug in 1, we're going to get 3.72 meters per second. This is the instantaneous velocity at 1 second. Okay, the tangent line. Anytime we're doing a tangent line, you need two things. You need the point and you need the slope. So my point is when t is 1, my position is 1.86, and then my slope we just found was 3.72. So we're going to have y minus 1.86, I guess that should actually be s, either way, is equal to 3.72 t minus 1. So we've got our slope, we've got our position, and then that should be an s there. So now we're going to find the velocity of the rock at any time t. So I'm going to use this as a model. Okay, this was specific to 1. Now I'm going to come up with a different thing, but it's going to model this. Okay, so the velocity is going to be the limit as t goes to, we're just going to call this t naught, some t value. We don't know what it is, but we'll just keep it as a variable, of s of t minus s of t naught over t minus t naught. So 1.86 t squared minus 1.86 t naught squared. Okay, so I'm going to pull out the 1.86, which again is going to leave me with the difference of squares. So I'm going to have 1.86 t minus t naught and t plus t naught. So these will go away. So we're left with 1.86 t plus t naught. So we're going to replace this for the t. So 1.86 t naught plus t naught. This is 1.86 times 2 t naught, which is 3.72 t naught. And that is the rate of the velocity at any given point t naught. So that's the average rate of change and how it relates to the derivative. We're going to spend a lot of time going over all sorts of things with derivatives, but this is just your introduction.